All right, good morning, chemists. Welcome back. This is chemistry 132B, quantum principles. Last week, week number 10. Very excited that we have arrived here and that we can actually conclude this course, hopefully in style and hopefully with, a good result on your final transcript. So this entire week, we will be spending on practicing problems that kind of like are representative of the exam that follows next week. So just to make sure that everybody is on board, the final exam is going to be next Monday, about the same time as now, 10:30, and the exam is 2 hours, so it will end at 12:30. And it will be conducted in Canvas in exactly the same fashion as you have done during the midterms. So there's no change there. So you'll be clicking on the quizzes. It will also be directly accessible under week 11. You see one single entry there, and you click on it, and then it will take you to the final exam. What we have to do is to get ready for this. And as I said, this particular week, we will not be introducing any new material. We'll just be rehearsing the stuff that we already talked about before. So it's evident that all the material covered in this class will be on the final exam. So the final exam is not just looking at the things that we've done after midterm 2. It's in fact covering all the material in this class. Okay, so it's cumulative. All the stuff together is on the menu. So that's why we want to take some time to go back to the beginning and basically walk through the entire class one more time, seeing some typical problems that you may expect. So this particular week, just to make sure that everybody understands, we do have homework. Okay, so that's homework for week 10, but it's not due on Sunday. It's due on Friday at midnight, so it's a little earlier. You may not like this, but I think it's important to get this done and not wait till the very last moment. So that over the weekend, in principle, you don't have to do homework. You can focus on different things. Ideally, preparing for the final, which will be on Monday, right after the weekend. It's not a lot of work, okay? So it's really, you can do the homework pretty quick, but please do it. The earlier, the better. You are already equipped to solve the questions at this point because we covered everything already, okay? So in fact, this particular homework will be about matrix diagonalization using this very simple software program online that we talked about last Friday in lecture. Okay, so using that program, you can diagonalize a matrix and then simply select the right results from the multiple choice questions. So I don't think it's a lot of work, but I think it's really instructive. If you do this, I think it really fosters understanding, and I think it will help you appreciate and understand the techniques that we talked about in this class. What else is happening this week? Well, we will be doing practice problems in class, so during lecture. That is what we will be doing right now after this slide. And in fact, there are practice problems already posted on the Canvas class website. So you can select those. I think it's about 10 questions or so. And this week we will be going through every single one of them and talk about all of them in lecture. Okay, so you will have the answers provided through lecture. In addition, there's also a practice final posted already on the class website. You can have a look at that, and the answers to that will be discussed in the discussion sections this week. Okay, so make sure you attend those. And at the very end of this week, we'll also be posting the key to the practice final. Okay, so we'll not be posting the key to the practice problems because we will go through them one by one in great detail in the lecture. And we will start, in fact, right now with that. Just before I move on, are there any questions of logistical nature that people like to see answered at this point? So make sure that everybody is on board. Everything's clear? Okay. Very good. Okay, let's move on then and look at the first practice problem. Like I said, the practice problems are posted on the class website, so you can have a look at that on your own. And this is the first problem that you will see. Okay, problem number 1. It says that we assume that there is an orthonormal basis set with n. So this is the particular notation that we have used. This is the cat notation. And n, of course, stands for the quantum number. Okay, so there's a whole set of them. N can be any number, any integer number that labels all the wave functions in that set. It's an orthonormal basis set. So we know what that means by now. It says that we have to find those statements that are true and assuming that m is not equal to n. So whenever you see an m, that is a different wave function, a different eigenfunction from the orthonormal set than n is. Okay, so they have different labels. Okay, so let's get started with the first one. We just have to say if it's right or wrong or true or false for each of these statements. First statement says m overlap integral with n equals 0. So if you really don't like the bracket notation, you can always translate this into a real integral. So there will be something like this. So eigenfunction, wave function, the label m. It's going to be complex conjugate times n, and then integrating over the entirety of space, the relevant space. Okay, so this is what the overlap integral is. It's the same as this bracket notation. And the bracket notation is a little, I would say, easier to interpret because you don't see all the bells and whistles. Simply knowing that this is an orthonormal set is sufficient to solve this problem. You don't need to know explicit expressions for these functions. That is the whole point of making use of the properties that an orthonormal basis set has. And one of its key properties is that every function in the set is orthonormal to all the other functions in the set. So if I have one function, let's say psi m and psi n, the other function, then I know for sure that they are orthonormal relative to one another. What does that mean? It means that they are orthogonal. And the definition of an orthogonal function, or two orthogonal functions, is that their overlap integral equals 0. So this is definitely true. So I'm going to select this one as a true statement. Okay, question number B. If this function is an eigenfunction of an operator A, then AMN equals 0. Okay, so what is AMN? It doesn't say anything about it, but I can assume that that must be something that looks like so. That is also an integral, right? It is basically the operator A sandwiched between m and n. It's m from the left and it's n from the right. So this is also an integral. If you don't like the bracket notation, then you can write out the whole thing if you want, although it doesn't contain any more information. But some people, they need to see this. Okay, so you can always write this. Okay, so that is basically the same thing, right? So that is what AMN is, and it says here that AMN must be 0. Now, how can I solve this problem if I don't have any extra information? Well, in fact, you do have extra information, very important information, because it says this function n is an eigenfunction of A. That means m is also an eigenfunction of A, because m is part of the same set. And if it is an eigenfunction, then there's a very specific relation. Okay, so that means if this operator is operating on n, then what it will do, it will generate an eigenvalue. What is the eigenvalue? I don't know, but it is some sort of value. I can give it any name, an, and it generates the eigenstate once again. That is the definition of n being an eigenfunction of A. Okay, it produces some kind of constant whenever the A operates onto this eigenfunction that I label with n. So that's what I know. So that's important because here I see this exact expression, A operating on n. So what I can say then if m n, this integral, is written as such, a is operating on n, so that will generate a constant or just a number, and then generate the eigenstate once again. Okay, so now since this is simply a number, I can take it out of this integral, and what I'm getting is this expression. Okay, so if you believe what we answered in question A, then this must be 0 as well. Okay, so I can be confident that indeed A m n must equal 0. So this is also a true statement. All right. Now we step it up a little bit, because now we have another operator that looks a little bit more complicated. This is a very funny construct where you first have this ket and then a bra, right? So that's just a definition. This is an operator. It's a funny looking operator, but it doesn't matter. You can just work with it and see what happens. It says that rho mn equals 1. Again, what does rho mn mean? Well, it's the same thing. Rho mn equals this thing sandwiched between the states m and n. Okay, so that is also an integral. So the operator is sandwiched between states m and n. M from the left, n from the right. So what do I know? Well, I do know what this operator looks like, so I'm just going to fill it out. I'm just going to fill it out. Okay, so this is m. The operator starts with a ket, then a bra. So I'm just going to write it, and then it closes the whole thing with this final guy right here. That is the final ket. Okay, so this is what I'm seeing, and these are basically two integrals. Right? The first one is 1 because it's an orthonormal set. The second one is also 1, function times itself, and another one, function times itself. So that must equal 1. Okay, so there's no clear mystery here. This must be 1, so that means that C is also right. Okay, so in this case, you really have to write it out. Unless you can see this directly, some people who have more experience in quantum mechanics, you can see directly, oh yeah, that must be 1. No problem, right? But if not, then you just want to kind of write it out on a piece of paper and make sure that you select the right answer here. Okay, D, final one for problem number 1. Also this same operator, but now a different kind of integral. Twice I have rho here. Okay, so what I'm going to do is I'm going to do exactly the same thing as I've done over here. I'm just going to write the whole thing out and see what I'm getting. Okay, so I'm going to write m, that's the first one here, and then twice rho. Okay, so this is the first row, and now the second row, m, n, and close it with the final ket, that's n. So this is what I have. Looks kind of similar to the last one, but of course this is quite different, because this is 1, that's a 1, but that's a 0. Okay, so I have 1 times 0 times 1, which of course equals 0. So the last one is not correct. Okay, so that's what I'm getting with these questions. There's a question. And the question is, could you please explain the notation on the option C, please? I'm not sure exactly which notation you mean. I have here rho. So if you want to understand how this should be interpreted, the only thing I can say about it, that this is a definition of what the operator is. A lot of people find this very funny looking. Okay, but remember, operators are things that do something to a function, right? That's what they do. So that could be anything. And so I can write this because this is a series of instructions, right? It simply says that if you have a function, so let's start with it. This is a function, okay? This is an eigenstate. And I'm going to do rho times the eigenstate. So rho is going to operate on this eigenstate. Okay, now rho is this set of instructions. The instruction is I'm going to multiply the ket from the left with the bra. Okay, And then when I'm done with that, I'm going to multiply it with this cat. That's just a series of instructions, right? So, that's what I'm going to do. So I'm going to first operate on n by multiplying this n with this bra from the left. And so when you do that operation, I get a result. Okay, and what I'm getting is m. I haven't worked on this m yet, but this is going to be 1. It's an integral 1, so this is times 1, and that's simply what I'm left with is this guy, right? So again, this operator's way of writing looks maybe weird, but remember, an operator is simply a set of instructions of what you're going to do to a function that you are given, right? Okay, there's another question about option D. Take each of the operators one at a time. Yes, right. That's exactly right. That's exactly what you do. You can take the operators one at a time, and that's what we did. What we did. We wrote this is the first row. This is row number 1, and this one is the row number 2. Okay, I wrote them out all at the same time. You don't have to, but that's what I did. And again, this is the 1. Then this is the remaining m from row. That's going to be multiplied now with, from the other end, the n from the first row. That's this guy. And so that is going to give me this integral n times m. And that's an overlap integral. That's going to be 0. Okay, so that is why I'm getting 0 here. Okay. Let's move to problem number 2. It's about spherical harmonic wave functions, YL, ML. Okay, those are the 2 quantum numbers. Remember, spherical harmonic wave functions are solutions for a particle, let's say our electron, on a spherical surface. Because it's on a spherical surface, there's wave functions that are bound because the spherical surface has boundary conditions. It must reflect back onto itself. And that leads to quantized wave functions, and they're labeled by 2 quantum numbers, L and ML. There's also 2 coordinates, right? Theta and phi, because the spherical surface is described by theta and phi. There's a little bit of symmetry between the number of coordinates and the number of quantum numbers. There's 2 quantum numbers for 2 dimensions. Right? This is kind of important to understand. It's not true that the L is the quantum number associated with theta and ML the quantum number associated with phi. That's not an exact 1-to-1, but there is a relation between the 2. All right, so L and ML are the 2 quantum numbers that quantize the wave function on the spherical surface. All right, that's just some general information. Let's move to the options here. Again, we have to select those statements that are true. Statement number A, or letter A, says the energy of YL, ML, theta phi depends on both L and ML. If you remember the expression for the energy of the spherical harmonics, then you know this not to be true. If you don't remember this expression, then you will find that expression actually on the exam, because there's going to be a constant sheet with constants and with the most important expressions and equations. And among those equations is the energy of the spherical harmonic. And if you find that on that sheet, which is provided on the final, so you don't have to look for it, you don't have to go online or you look at your notes, it's already there. You will find this expression, and hopefully that expression looks very familiar, because that is the solution of the spherical harmonics. Okay, so L and then L plus 1 between parentheses is what my quantum number is going to do. So that basically quantizes the energy. Okay, so the energy is quantized here by L. There's no ML in there. Okay, ML is not there. And that means that the statement itself is not correct, because it only depends on L. The energy only depends on L, not on ML. Okay, that is important to understand, because that's very fundamental. Okay, the energy is on the the spherical surface are only quantized through L and not through ML. That means that ML are different solutions for a given L, but those solutions are degenerate. Think about the P wave functions. Okay, there is two, and there's actually for L equals 2. No, let's not say that. L equals 1 is a P wave function. L equals 1 is a P wave function. Let's write it down. That corresponds to a P wave function. We know there are 3 P wave functions, right? Because they have ML -1, 0, and 1. Those are the possible solutions, but they all have the same energy, right? They are degenerate. The energy of the p orbital only depends on what L is, not on what ML is. They are degenerate. That's another way you could have figured it out. You don't even have to look at this. You can just think about what you know about p orbitals, for instance, or d orbitals for that matter, when L equals 2, because then you have, of course, ML. There's 5 versions of that, but they all have the same energy, -2, -1, 0, 1, and 2. 5 different d orbitals, but they all have the same energy. So therefore, ML does not determine the energy of the states, right? That is all through the spherical harmonics. All right, next one. YL, ML, theta phi is an eigenfunction of this operator, which is the magnitude of angular momentum, orbital angular momentum squared. That is the operator. If you know this, then you know, of course, that this is a true statement. There's several ways to figure this out. The one that I prefer is the following. I know the energy, actually not the energy. Let me, let me say the Hamiltonian kinetic part of the Hamiltonian. So there's no potential energy, V equals 0. The energy on a spherical surface is always, in this case, determined by the kinetic energy, which can be written as something that goes like this. It is the angular momentum squared divided by 2 times m, right? Where m is the mass, but in spherical terms, that's going to be the moment of inertia. So what I'm having is an expression that looks like this. This is always true. This is also true in classical terms, where this L squared is the orbital angular momentum, and without the little hat, okay, because it's classical, but it's the same expression, right? So L squared is momentum, angular momentum squared, divided by 2I, where I is the moment of inertia. This is always true. This is the kinetic energy of a particle moving on a spherical surface. Always, both classically and quantum mechanically. The difference being that quantum mechanically, this L squared is quantized because it's determined by an operator and not by a classical quantity that is continuous and can have any value. In quantum mechanics, it can have only certain values. All right, that's why it's determined by an operator. But the physics is the same. So if the spherical harmonics are eigenfunctions of the Hamiltonian, which they are, because that's how they were solved in the first place, then they must also be an eigenfunction of this operator L squared, right? Because the only difference between L squared and a Hamiltonian is simply a factor 1 over 2I, where 2I is a constant. It's m times r squared, which is a constant, okay? So that is not determining whether or not something is an eigenfunction or not. So another way to do it, if you have the time, you can figure out that this commutator is 0, which means they have the same set of eigenfunctions. Why is this 0? Because L squared is part of the Hamiltonian. This is not an operator, okay? So only that is the operator. That means they must commute, and therefore they must have the same set of eigenfunctions. Okay, so option B is definitely true. All right, spherical harmonics. This function here has L angular nodes. L angular nodes. This is a question that was on midterm number 2. Remember this? You have to determine the number of angular nodes of a given spherical harmonic function. And the answer is that you have L angular nodes for a given spherical harmonic function. So this is also true. This is also true. think about, again, a p orbital. A p orbital has L equals 1. A p orbital has one angular node, straight through the middle. That's why it looks like a dumbbell. That is one angular node, that's one plane. Angular nodes are actually planar nodes, right? L equals 2 is a d orbital. D orbital has two angular planes, two angular nodes, sorry. And that's also a plane. So two planes that form nodes. That's why they have more interesting shapes than p orbitals. Think about the four-lobed pattern of most of the d orbitals. That's because they have two nodal planes, two angular nodes. So the number of angular nodes scales with L directly. If L equals 1, there's one angular node. If L equals 2, there's two angular nodes, and so forth. Okay, the functions y1, 1 and y1, -1 are not orthogonal because they have the same quantum number L. That's an interesting statement, but it's unfortunately not true because L is indeed the same, but ML is different, and that is going to be important because these are different functions because they have different quantum numbers, and different functions from the same set must be orthogonal. Otherwise, they are not different functions from the same set. Okay, that is an intrinsic definition. Any of the functions of the circle harmonics are orthogonal to any other function within the set. Okay, and since these are two different functions labeled by two different MLs, they must be orthogonal. So this is not a true statement. Don't be fooled. This is a kind of a question that's trying to make you think that this is true. Because you say, well, the same quantum number for L, that is okay, but ML also has to be the same for these two functions to overlap into a finite integral. If not, they are having no overlap, therefore they are orthogonal. Okay, problem number 3. Consider the eigenstates V of the quantum harmonic oscillator. So now we're talking about the quantum harmonic oscillator. We haven't talked about it in a while. It's still there. So let's brush off some dust from our knowledge here about quantum harmonic oscillators. Again, we have to select the statements that are true. All right, first statement. The energy separation delta E between two different states of V. V is, of course, a quantum number, so there's a whole set of these states. The difference in energy between these states, it says, grows larger if the spring constant K increases. Okay, so again, if you see a question like this, I would go immediately to my sheet that is provided on the exam that has all the relevant formulas, and from that you will be able to figure this out. Okay, because the energy E, okay, of an harmonic oscillator is V plus half times H and omega, right? And the thing is that omega here, this is important, equals square root Kf, which is a spring constant, over m, which is the mass of the particle that is in the harmonic well. So this is Kf, that is a spring constant. So the square root goes over the entire thing, okay? So it's a square root of Kf over m. So that is the K that we are talking about. So that's the relation, but this is E, this is not delta E. What is delta E? Well, that is basically the difference between two subsequent states. All right, and maybe you remember that, but if you subtract, let's say, state number 1 from state number 2, then what you find, or state number 0, because V equals at 0, then what you find is that the delta E, and we have done this several times in class, delta E is always H bar omega. No matter what the V is, okay, between subsequent states, between consecutive states, the energy difference is H bar omega. Right? I can fill out, for instance, V equals 0, and then V equals 1, subtract these two energies from one another, and I'll find the energy difference is H bar omega. The same is true for any set of consecutive states. All right. All right, so basically this is what it is. The delta E is directly proportional to this omega, which is directly proportional to the square root of Kf over m. So if Kf grows larger, that's what it says, if K increases, then omega gets bigger too. That means that delta E is going to be bigger. Okay, so this is true. That must be a true statement then. What does it mean physically? That's also important. Physically, if K is going to be increasing, that means that the spring is going to be a lot stiffer. The larger the spring constant, the stronger the force that, that is a force that basically brings the system together, restoring force. The restoring force is stronger if K is increasing. And if you have a very stiff spring, okay, that means that the system is very contracted. That also means that the potential well is very skinny. You have a very skinny potential well. And that means, of course, that the system is more confined. If the system is more confined, that means that the separation between states is going to be increasing because you get more quantum mechanical character. The shallower this potential well is, the more classical it becomes. And therefore, the separation between states is decreasing. So the more classical it becomes, the smaller the separation between states, but the more quantum mechanical it becomes, the larger the separation between states. And the stiffness of the spring is directly related to this. Oh, I didn't even put on my video. Okay, here we go. Statement B, the energy separation delta E between states grows larger if the effective mass m increases. This is something I can also answer directly from the last question because I have the same expression here. Now I'm looking at m. If m is increasing, because it's the denominator here under the square root sign, that means that if m is increasing, that omega is going to go down. If omega is going to go down, then the energy separation is going to go down as well. So clearly, this is not true. Okay, the separation does not grow. In fact, it shrinks if the effective mass m increases. So what do we make of this? Physically, well, physically, it also makes a lot of sense because if m increases, that means that the system becomes less quantum mechanical. Quantum mechanics is prevalent for very light particles. The quantum mechanical character increases for lighter particles. So when m goes up, the quantum mechanical character decreases. And that's exactly what is reflected in these formulas here. When the m goes up, delta E is decreasing. That means the states get closer and closer and closer. It becomes more and more classical till it forms a continuum of states, which basically is indistinguishable from a classical situation. Real quantum mechanics means very discrete behavior, nothing in between the states, large separation. That's really quantum mechanics. The closer you are, the more you are approaching the classical limit. Okay, this statement here, statement C, it's an integral again. This is basically the expectation value of this operator x. Okay, and it says 0. So if I calculate this integral, it's basically the expectation of the operator x, which is the position operator, then I should be finding 0. This is something you cannot compute because you don't know which state v you are talking about here. So there's no way you can do this by real nitty-gritty mathematics because you don't have the information. So we have to use a physical argument to address this question. This is really kind of a question that relates to how much I know about the problem. Do I really know the physical meaning of this problem? So this is the mean value of x, which means the mean position of the particle when it's a harmonic oscillator. Okay, and so if you have an harmonic oscillator, this is the potential well. You know these wave functions, they have certain shapes, right? This is what they look like. And the question is, what is the mean position of this particle when it sits in the well? Well, all these functions are symmetric or asymmetric. Okay, and if I look at the wave function squared when it sits in the well, then they are all symmetric around x equals 0. Okay, That means that they spend as much time on the left as they spend time on the right. That means on average, it is going to be 0. This is a true statement, all right? So the average position of the particle in the well is 0. That means the expectation value of the position is 0 by a symmetry argument that it spends as much time on the left as it spends on the right, because all the functions, psi, modulus squared, are symmetric around 0. So physically, that makes also a lot of sense, of course, because you know any oscillator, if it's symmetric, it moves as much to the left as moves to the right. On average, of course, spends, you know, it has its average going to be exactly in the middle. All right. This is true also classically. There is in principle nothing quantum mechanical about this. So this is true for a classical pendulum as it is for a quantum harmonic oscillator. The average position is going to be 0 based on a simple symmetry argument. All right, this question here looks very similar, but now I have this operator. That's the mean square displacement. The mean square displacement. This has a different physical meaning. What is the difference? If I have my harmonic well, this is my first wave function. And if I go up the ladder, this wave function becomes more complicated. They have, you know, wiggles, but then in the middle, the wiggles are very little. And then at the end, the wiggles are stronger. You see there's more density at the edges now. It becomes more and more classical because it spends more time near the edges than it does in the middle. Okay, x squared is proportional to that phenomenon. It is proportional to the mean square displacement, saying what is the density of the wave function as a function of space. You see the density goes up near the edges for higher quantum numbers. Okay, that is what mean square displacement means. It's not the average. It's not the average. It is how much density you have as a function of space. And it's, you can see here that that is not going to be 0 because you have more density away from 0 than you have at 0. Okay, so that is really what the physical meaning is of mean square displacement. Classically, that's the same as well. If you have a pendulum, it spends more time at the edges because that's a turning point, and it basically spends very little time in the middle because it zips through there at high speed, right? And the mean square displacement, therefore, the mean square displacement is much larger if you have larger amplitudes. So the amplitude of the pendulum is going to go up if you give it more energy. That is the meaning of the mean square displacement. It's therefore not 0, and therefore this is going to be incorrect. So distinguish, please, the meaning of the mean, the average position, and the mean square displacement. This displacement of the oscillator relative to its equilibrium position grows if it has more energy. Right? It's a different physical meaning than the mean position of the oscillator. Okay, question number 4. Consider the molecular orbitals of HF. Now we're going to talk about molecular orbitals. So quite different, right? So we're jumping around here, but we have to know, of course, a little bit about all of these topics. HF is hydrogen fluoride, and we have to, again, determine which of these statements are true. These are all conceptual questions. We haven't really calculated much. No values have been put in here, okay? So this is all just understanding quantum mechanics. Okay, statement A. The molecular orbital is formed between an s atomic orbital from hydrogen and an s atomic orbital from fluorine. And that does not sound really right to me. Okay, so I know that if I have the 1s from hydrogen here, the energy of F is a little lower, but the orbital that is the highest in fluorine, that it has an electron available for bonding, is the 2p, not the 2s. The 2p are having the electrons. There's one 2p orbital with one electron. That electron is available for bonding. And so those are the states that are going to make my molecular orbital. It's an asymmetric situation because the energies are not the same, right? The energy of hydrogen is higher than the 2p energy of fluorine. these two electrons form a bonding orbital, or they occupy the bonding orbital of the molecular orbital set, where this one I can call plus, and this one I can call minus, the molecular orbitals. So it's definitely not true that you need an s atomic orbital from fluorine, because the s atomic orbital from fluorine is way lower in energy and is fully occupied, so is not really ready to engage in the bonding. So this statement is incorrect. Okay, statement B. The F atomic orbitals are sp2 hybridized before forming a molecular orbital. This is not necessary. You don't need to hybridize the atomic orbitals for fluorine. Why not? Because the atomic orbitals 2p have the correct symmetry already to engage in an on-axis bond with hydrogen. So the hydrogen will not perturb the fluorine enough so that the fluorine has to accommodate the bonding pattern through hybridization of its atomic orbitals. This is not needed in this case. All right, so typically the hydrogen is insufficiently perturbing the fluorine atomic orbitals to force them into a different hybridization state. Okay, the 2p orbital, atomic orbital, unperturbed orbital of fluorine is sufficient to understand the bonding between H and F. So this one is not true either. Okay, the H and F atomic orbitals, this is C here, contribute different weights to the molecular orbital. This is true. In fact, okay, this is a heteronuclear diatomic, and you know, H and F are very different orbitals. 1s from H, 2p from F. So there's no guarantee that the atomic orbitals that form are formed from exactly 50% of H and exactly 50% of F. That is very unlikely. And you can already see here that this is a highly distorted asymmetric bonding and anti-bonding molecular orbital, right? So this molecular orbital diagram shows the asymmetry, and that insinuates that H and F contribute differently to the formation of the molecular orbital. We don't know exactly what those numbers are. Okay, we don't know. Actually, we have looked at it in class, and we have written out, and you can go back to one of the lecture notes, and we have actually written out those coefficients, and you can see indeed those coefficients are not the same for H and F, right? So we don't have to determine those numbers here. We just have to recognize that this is an asymmetric situation here, and that therefore H and F contribute differently to the formation of the molecular orbital. Okay, D, because HF has a heteronuclear bond, that's true, bonding and anti-bonding orbitals do not have to be orthogonal. All right, what does that mean? Well, when we form molecular orbitals, when we form molecular orbitals, yes, we form an anti-bonding and a bonding orbital. These are two new states. And for these two new states to be appropriate descriptions, they need to be orthogonal relative to one another. That means psi plus has no character of psi negative, psi minus, right? They are completely independent solutions. If there is an overlap between the two, that means that there's a little bit of character of anti-bonding in psi plus and a little bit of bonding character in psi minus. That's what it means. But we require that not to be the case. We want these two functions to be completely orthogonal, so they describe unique states. There's no overlap between these states. All right, so this is an important consideration. If we form molecular orbitals, we want those molecular orbitals to be unique solutions that have nothing to do with one another, and therefore they must be orthogonal. Okay, so that is what we require. Now, this is a heteronuclear bond, so the question is, does a heteronuclear bond some way, somehow changes that requirement? And the answer is no, none of that, because in terms of quantum mechanics, this must still be true. Okay, the overlap integral of this guy, the anti-bonding and the bonding, must be 0 for them to be unique solutions to my problem. Right? So this is the overlap integral S, and we want this overlap integral to be 0 for them to be unique solutions, irrespective of whether this is a homonuclear or a heteronuclear bond. There's no difference between the two scenarios. Okay, wow, it's already time. We've got a couple of minutes left. I'll leave it at this problem. We have many more problems to discuss, but fortunately we have 2 more lectures. So we'll go through them step by step. Let me know if there's any questions about the questions we have discussed so far. If anything is unclear, let me know. No? Yes, D is false, correct. D is incorrect. Yeah. Can we go over 4b again? Yes. This is 4b. It is about hybridization of atomic orbitals. Now, the point is, what exactly is hybridization? I mean, it's really, I think, important for us to understand what it is, because it falls a little bit out of the blue sky. Sometimes we have hybridized states, sometimes we have not, and it's kind of like arbitrary. So what is the meaning of all of this? Well, the meaning of hybridized atomic orbitals is, first of all, it's an atomic-centric theory. Okay, so valence bond theory is an atomic-centric theory, meaning that it looks only at one atom. So in this case, it looks at F. But in general, it looks at the central atom of a structure, right? And the question is, what happens if that central atom is surrounded in a certain way by other atoms? We know that if you put other atoms nearby the atom of interest, that the charges that you introduce will change my entire system. And therefore, the atomic orbitals that were solutions of the Schrödinger equation of the isolated atom are now going to be different. And the differences then are described by forming hybridized orbitals. So the hybridization is a theory that helps us understand how different atomic orbitals can be if you put an atom into a different situation with new charges around it, new atoms that are surrounding our atom of interest. And it does a great job at predicting what the symmetries should be. Now, this is true in general, okay, but it doesn't always have to be true. When do we not hybridize atomic orbitals? And that is when there is very limited reason to do so. When there's very little perturbation, when you only introduce a small charge such that the atomic orbitals barely change. There's no real response in reordering the entire symmetry of the problem. And that's the case in things like this. Typically for terminal bonds, okay, for bonds that are terminal. So there's no 2, 3, or 4 bonds. There's only one bond. And even one bond arrangements, oftentimes, not always, but oftentimes, it is insufficient to completely alter the entire structure of atomic orbitals. It's a small perturbation. And that is the case here as well. The p orbitals of F, the atomic unperturbed orbitals of fluorine, are perfectly oriented and have the perfect symmetry to explain the bonding with H. So the H atom getting closer to F does not have the power to completely alter the atomic orbitals of fluorine. Won't do it. It's a very mild perturbation, and the symmetry of F stays the same. So these are pretty much the same orbitals as they were for F in isolation. So that's why. And this is generally true for terminal bonds that are single bond. For single bond terminal bonds, in general, we don't need to do hybridization. Now, for double bonds terminal, like carbonyl, for instance, carbonyl bond, it's a little different story, because there you need a double bond, and therefore the hybridization of the oxygen typically is required to explain that. But here, for the single bond terminal group, we don't have to do that. How many questions does the final have? I don't remember by heart, but I can tell you for sure that, and I'll give that number on Wednesday to be more precise, but the number of questions is not very high, and you'll be able to complete it in 2 hours, no problem. It's less than twice as long as the midterm exams, but you have 2 hours, so you will definitely be finished before time's up. So I don't think that this is going to be a problem. I don't think anybody will be pressed for time. Okay. Okay, so yeah, we talked about conceptual questions in this lecture, but there will also be, of course, questions where you have to compute stuff. And we will go through some examples. Wednesday and Friday we'll have more examples. And you see some of them will be numerical. So we have to be able to do both, right? But these conceptual ones are important. A lot of students have a hard time answering these questions correctly, and they'll lose a lot of points. And so this is where I hope you can focus your attention, make sure you really get the concepts right.